Hey everyone, Houston Math Prep here. We're going to expand on our last video, which was finding area using double integrals. Here we're going to talk about finding volume with double integrals. Here I've got my double integral over some region R dA. Remember, we can think of that as the double integral over some region R, either dx dy order for iterated integral or dy dx. And remember that this is calculating area, right? Either of these, whichever order you decide to integrate dy dx or dx dy, you are calculating area. What we haven't really talked about is the function that's actually inside of these double integrals. If you think about what's actually in there, we actually have a function of 1 that is inside of each of these. So these expressions are the same thing as saying the double integral of 1 dx dy over the region, or the double integral of 1 dy dx over the region. And so think about what that's really saying. The idea here that we have some double integral dA that symbolizes the area for our region R in the plane. And these, if we really think about having a 1 inside, which is the exact same thing, that's really like summing up the value 1 at every single point. And if we think of that additional dimension of thinking a value of 1 at every single point in this region, it doesn't change the calculation, it stays the same. But we can think of this as a region that has a height of 1 at every point. And then we begin to start seeing this as volume rather than area. Now, obviously, if you have the area of the base and a volume of an object that is 1 unit tall everywhere above that same base, then of course those things are going to be equal to each other. But what if instead of having just a height of 1, what if we had many different heights? Lots of different heights over all of the different points in our region R, thinking of that height being like a function. So what if instead of having a height function of 1 inside of our double integrals, what if we had some height function that was a function of x or y, or both? And so each point, x comma y, in the region R had that function value. Well, if we summed up a bunch of those heights over that region R, then that's going to allow us to calculate volume with our double integral. Let's look at our first example here. We want to find the volume between the xy plane, so we have the bottom of my object here, and the plane z equals 6 minus 3x minus 2y. So we're going to set up our volume to be a double integral. So our volume is going to be a double integral, and what we'll need is we'll need our height function inside of this integral. So inside of our double integral, we're going to say that we are going to integrate the function of xy, which is 6 minus 3x minus 2y. So that's the function that gives me the top of my solid here. That's my height function. And we'll need to choose dx dy or dy dx here. So let's go ahead and think about the shape of my region, the shape of my base. Well, if that's the unit square, then what we really have is just basically from 0 to 1 on the x-axis and from 0 to 1 on the y-axis. And so our region is just this square inside of this area here. And you can tell that this is simple in the x direction and the y direction if you looked at our video on double integrals to find area. So it doesn't really matter. I'll just go ahead and choose, let's say, dy dx in this instance. And then once I do that, I just simply need to find my bounds. Now, obviously, since this is a square or a rectangle, we're going to have constant bounds both directions. So in the y direction, which is our inside integral, our inner bounds are going to be from 0 to 1 for y. And our outer bounds will be from 0 to 1 for x. So this double integral here with the function inside represents the volume of this solid object we have pictured here. Okay, let's go ahead and begin to compute this integral. So first I will write down my outside 0 to 1 and evaluate this inside integral here, dy. So if I integrate dy, 6 will become 6y, negative 3x will become negative 3xy. And then power rule for the y here, we'll get y squared over 2, and the 2 will reduce with the minus 2, so we'll get minus y squared. And then we will evaluate from 0 to 1 for y, and dx will be our next step. So let's go ahead and plug in our bounds. So we will have, plugging in 1, we will get 6 times 1, which would be 6, minus 3x times 1 would be minus 3x. Minus 1 squared, which would be 1, minus, and then if we plug in 0 for y, notice every term has a y in it, so each of those terms is going to be 0. So we'll get 0 for all of those, and then we'll have that integrated dx. Okay, let's go ahead and clean this up a bit. So we'll say the integral from 0 to 1 of 6 minus 1 is going to give us 5 minus 3x minus 0 won't change anything. And now we will integrate this dx, so we will get easy integration dx here. We'll get 5x minus power rule. Power goes up by 1, divide by the new power, so x squared and divide by 2 gives us 3 halves here, and an x squared, and then we'll evaluate from 0 to 1. Let's plug in those bounds. So if we plug in 1, we'll get 5 minus 3 halves. And plugging in 0 for x, we'll get 0 and 0 here, so minus 0 there. And 5 minus 3 halves, 10 halves minus 3 halves, is going to give us 7 halves. 7 over 2 will be the volume of my solid object here. Let's look at another. We want to find the volume of the tetrahedron, this shape here, in the first octant, so that's where x, y, and z are all positive, bounded by this plane 4x plus 2y plus z equal to 8. So we want to set up our volume as a double integral, so our volume will equal double integral here. And what I want to do is think about my height function. Well, that's 4x plus 2y plus z equals 8 is this top piece here, right? That plane there. So, but the question is, what is it as a function of x and y, right? What is it in terms of z equals? So if I rearrange this in terms of z equals, then I would move these two terms over, subtract them to the other side. That's going to be z equals 8 minus 4x minus 2y. So that'll be my height function. Remember that if you need to solve for z and get it explicitly, then make sure you do that first before you set up your height function in your integral. So now we'll need to decide if we're integrating dx dy or dy dx, what order we're doing. It'll be dependent on the shape of this region that's the base here. I think we can see it's triangular, right? So if you go ahead and think about what's going on, I have the axes, right? Certainly this is in the xy plane. Under the first octant would be my first quadrant. And I have this sort of diagonal line that's making a triangular base, right? So this is the shape of my region that is my base. This line here is where the top of my tetrahedron, this z equals equation, hits the xy plane. Now that's when z is equal to 0, right? So this line here is going to be when we have 0 equals 8 minus 4x minus 2y. If I move the x and y term to the other side, in other words, that's when 4x plus 2y is equal to 8. Okay, so it is a line, we can tell that, and it's going to be simple in the x direction, and it's going to be simple in the y direction. So we'll go ahead and set this up, maybe dy dx again. You can do either order you like. I'm just picking this one. Okay, if I set up dy dx, now I need to figure out my bounds. So that says fix an x and draw through in the y direction. So we'll go ahead and choose an x value, let's say an x value right here, and draw through in the y direction. I enter the region on the horizontal axis, which is going to be at 0, and then I exit through this diagonal line. So this lower bound will be y equals 0, and this upper bound will be y equals whatever the equation for this line is. So what I would need to do is solve this in terms of y. So I would subtract 4x to the other side, divide by 2, and the form that I want this in will actually be y equals negative 2x plus 4. That will be the line here. So we'll go ahead and say negative 2x plus 4 is our upper bound. And remember, for our outside integral here, we just need constants for our bounds. So these would be x bounds, so x equals for both of these. Now obviously this leftmost part right here is x equals 0, and then to figure out what this rightmost point is, our largest value for x, we could simply set y equal to 0 since that's an intercept, and we could figure out what x is, and it turns out that x is equal to 2 at this point. So we're integrating from 0 to 2 for our outside integral here. Okay, now that our volume integral is set up, we can go ahead and begin to integrate this. So we'll have from 0 to 2 on our outer integral here, integrating from 0 to negative 2x plus 4 dy. Let's go ahead and do this inner integral here. So if we integrate dy, 8 would become 8y, negative 4x would become negative 4xy, and then power rule, raise the power by 1, divide by 2, so we would get minus y squared. and plugging in our bounds from 0 to negative 2x plus 4. We will then integrate all of that dx. Okay, let's go ahead and put in our bounds. So we will have, I'm going to start over here because I have a bit of stuff. Notice I have two terms to plug into for y everywhere here. So we have the integral from 0 to 2, and since I have a bunch of stuff to plug in, I'm going to go ahead and start with curly braces out here. So plugging in the upper bound here, negative 2x plus 4, which will be some work, we'll have 8 times negative 2x plus 4 minus 4x times, again, negative 2x plus 4 minus negative 2x plus 4 all squared. So that's plugging in negative 2x plus 4. And then plugging in 0, I have a y here, here, and here, so it would be minus 0 for all of those terms. Okay, so all of that, we're going to have to do some distributing and cleaning up here, but we'll do it. Okay, integral 0 to 2. Let's go ahead and say negative 16x plus 32, distributing the 8, distribute the negative 4x, we'll get plus 8x squared minus 16x minus, and then let's go ahead and do our square here. So this thing times itself will be 4x squared. 2ab is going to be negative 16x, and then this thing times itself will be plus 16 if you distribute all of that out. Have to integrate all of that dx. Let's go ahead and combine some like stuff here. So I've got 8x squared minus 4x squared. That'll give me 4x squared, so those are taken care of. We have negative 16x minus another, but then plus a 16x, so it actually just gives us minus 16x total. That takes care of all those. And then 32 minus 16 would give us positive 16. So we're going to go ahead and integrate that dx. You could, factor out a 4 and bump it out if you want. We'll just go ahead and continue from here. So if we now integrate dx, then we will get the power going up by 1, and we'll divide by the new power, so that will be 4/3 x cubed, minus power goes up by 1, we'll divide by 2 then, so we'll get 8x squared plus just 16x for the last one, and evaluating from 0 to 2. And if we go ahead and plug in our 2, then that will give us 4/3 times 8 minus 8 times 4 plus 16 times 2. And there's an x in every term here, so all of those will just be 0. And so we'll get 32 over 3 minus 32 plus 32. So I think we can see that's going to give us 32/3, right? 32 over 3 for this volume. For our next one here, we're going to find the volume under the graph of z equals x squared above a triangular region here with these vertices. You can see this kind of has a parabolic bend to it based on this z equals x squared. So this is my x-axis, my y-axis, my z-axis here. And so we have a triangular region. Let's go ahead and set up our volume integral. So volume is going to equal double integral. And my top surface here is z equals x squared. It's already solved for z, so we're good. We can just put x squared in our integral. Let's go ahead and look at the shape of our region. So if you think about, here's the y-axis, and here's the x-axis. And so we have something that looks a bit like this. And so here's my 1, 0, here's my 0, 1, and my 0, negative 1. So this is my region R, this triangular region. And we want to figure out, is it x simple, y simple? If I draw through in the x direction, I'm going through the vertical line, but then this diagonal line here, down here, I'm going through a different diagonal line. So those are different rules, I think. So we want to go the other direction. If I choose an x and draw through in the y direction, I'll always be going through this slant and always coming out this slant. So this is y simple instead of x simple. Since it's y simple, then we'll go ahead and integrate dy first. You can check out some more details on that from our previous video on finding area with double integrals if you like. And now we need to set up our bounds. So if I, just like I said, choose an x and draw through the region in the y direction, then I go through this, I enter the region, on that diagonal, I leave the region on that diagonal, right? So I need to figure out equations for these, and since it's dy, these need to be y bounds, right? Y equals, these will be x equals, obviously out here based on our order of integration. So, well, let's see, it goes through 0, -1, and then it goes through 1, 0. So it goes up 1 over 1, so it has a slope of 1, and it goes through 1 unit below the axis, right? So a slope of 1, intercept of -1, then that means this is going to be y equals x minus 1. So that's that. And this one kind of a different thing, right? If it goes through here and here, it has a slope of -1, but it has an intercept of +1. So that's the same as saying -x plus 1. Based on its slope-intercept form. Let me turn that around, and I'll just say 1 minus x. That's a little nicer than having the negative in the front, but you can say -x plus 1 if you want. Okay, now we just need to assign our constants for x. So obviously, the left side of my region is on the axis, so that's going to be x equals 0. And then this farthest point to the right here is at 1, 0, and so we know that the farthest right value for x is going to be 1. And so this is our volume integral with our top surface formula x squared. Okay, let's go ahead and start to evaluate this. So we'll copy down our integral 0 to 1, and then we'll begin to evaluate. So we're integrating dy on the inside here. If I integrate x squared dy, I just get x squared y. Our bounds are x minus 1 for y and 1 minus x for y. And then we'll integrate that dx. Okay, so we still have our integral from 0 to 1. Let's plug in our bounds now. Remember, we're plugging in for y, so this would be x squared times 1 minus x if I plug in the top bound, minus x squared times x minus 1 if I plug in the bottom bound. And let's do a little distributing with that. So integral from 0 to 1, we will have x squared minus x cubed plus x squared. So definitely some common terms that we can simplify there. Let's go ahead and write that. So we'll have the integral from 0 to 1, and we will end up having, let's see, 2x squareds, and then we have negative 2x cubes. We'll integrate that dx, and that'll be no problem for us. So power rule tells us that goes up by 1, divide by the new power, so I'll be dividing by 3 and have a power of 3. Minus here, power goes up by 1, I'd divide by a 4. 2 over 4 would be a half, so I'd get half x to the 4. And now, plugging in bounds 0 to 1. Well, let's see, plugging in 1 is just going to give me 2/3 minus 1/2. Plugging in 0, since there's an x in each of these, that's just going to be minus 0. And if you get a common denominator, this is 4 over 6, and this is 3 over 6, and 4/6 minus 3/6 is going to give you 1 over 6 for this one. So here we're going to do something just a little bit different for our last one. We want to find the volume of the solid bounded above by the plane x plus y plus 2z equals 6. So that's this plane here. Below, not by the xy plane, but by the plane y minus 2z equals 8. So we have another plane down here, this triangular region down here, triangular region up here, so we are sandwiched between those. And then it is also bounded on the sides by the xz plane, which is this flat space here, and then the yz plane, which is this flat space back here. And x plus y equals 6 is this vertical surface here, the kind of side that we're looking through into the solid object here. So we want to find the volume of that, but we're not doing just something above the xy plane that is bounded above by a function. We're actually doing something that is bounded between two functions. And so if you remember doing in single variable calculus, area between two curves, you did the integral of the top minus the bottom whenever you did area between instead of just area above the axis. So that's what we're going to do here. We'll have a top and a bottom function. We need to do top minus bottom. So our volume for this one is going to be basically our double integral over the region, and then we're going to do simply top minus bottom function in terms of z, and then we'll integrate that either dx dy or dy dx. Okay, so our top and bottom functions, we'll need to make sure we have those solved for z, so we can plug those into our integral. Our top function, here it says the solid is bounded above by this plane, so that's our top, this x plus y plus 2z equals 6. We need to solve that for z. So we would subtract the x and y to the other side and then divide by 2. If you work that out for a second, you'll see that we get z equals 3 minus a half x minus a half y. So that's going to be our top. And then we'll have to subtract the bottom function. So our bottom here needs to be, again, z equals, right? So if we do that, then we'll get 1/2 y minus 4. So we'll have to do this top function minus this bottom function, and then we'll also have to decide on our bounds. So let's go ahead and start to plug this in. So we have our volume is going to equal my double integral. I'm going to wait on bounds because I need to choose my order. So we'll go ahead and say top minus bottom will be 3 minus 1/2 x minus 1/2 y. That's my top minus my bottom, 1/2 y minus 4. All of that integrating dx dy or dy dx. So let's think about the shape of my region in the plane. If you sort of look straight down at this from above, you're going to see we get a triangular region again. And this diagonal piece right here sort of gives us the shape of what the region is in the plane. So you can think about that's the shadow it casts in the plane, the xy plane. And that is the line x plus y equals 6 here. X plus y equals 6. So you might be able to tell pretty easily they're both going to have intercepts of 6, right? So we have this nice region that is triangular. It's x simple, it's y simple, it doesn't really matter. So I'm just going to go ahead and choose dy dx again, we'll say. If I've chosen that, that means I need to fix some x value and draw through in the y direction to choose my bounds. So if I say this x value and I draw through in the y direction, I would enter the region at y equals 0, so 0 will be my bound here, and I leave at x plus y equals 6. But now if my inside integral is dy, I need this solved for y. So we could go ahead and say y is equal to 6 minus x if we want. So from 0 to 6 minus x, that's our inside integral bounds. Let's go ahead and do our constant bounds on the outside. My leftmost value here is at 0, so x equals 0 is my lower bound, and obviously over here we set at 6. So from 0 to 6 for my x bounds on the outer integral. So now we'll go ahead and evaluate this. Let's go ahead and actually do some combining of like terms before we do anything with this. So let's say, okay, from 0 to 6 and from 0 to 6 minus x. But I'm going to go ahead and say 3 minus negative 4 is 7. That's the only x term I have, so I'll keep minus 1/2 x. Minus a half y minus another half y is minus a whole y. And then we can integrate this dy dx. Okay, let's move on to the antiderivatives. So we're going to go ahead and do the inside piece here, integrating dy. So we'll leave the 0 to 6 integral out here. Antiderivative with respect to y, we get 7y minus 1/2 xy minus, and then 1/2 y squared from the power rule. And we'll evaluate from 0 to 6 minus x, and dx will be our next step. Okay, so it looks like we're going to have some distributing to do, and I plug 6 minus x in for y, so let's go ahead and do all that. So from 0 to 6 here, we're going to have plugging in 6 minus x for y, 7 times 6 minus x minus 1/2 x times another 6 minus x minus 1/2, and then here we have y squared, so 6 minus x all squared. That's the first part, plugging in the top bound. Plugging in 0, we have y in each term, so we're just going to get minus 0 for all of those. So that saves us a bit, right? Okay, let's do our distributing, and we'll keep going. So from 0 to 6, we will get 42 minus 7x minus 3x, distributing here, and then we'll get plus 1/2 x squared. minus 1/2. I'm going to distribute my 6 minus x 2 copies first before I use my negative 1/2. So I'll get 36. I'll get a minus 6x, and another minus 6x would be minus 12x plus x squared. All of that dx. All right, we're going to do this in more than one step, I think. We'll hurry along with it, though. So we get 42 minus 10x plus 1/2 x squared minus 18, distributing the half, plus 6x minus 1/2 x squared. So the nice thing, I guess, we get here is that the x squared's reduced to 0, and then we just have some constant and some x left over. So we have 42 minus 18, that'll be 24 there, and then negative 10x plus 6x will give us minus 4x. And we'll integrate that dx from 0 to 6. So integrating 24, we get 24x minus power rule, x squared divided by 2 would make a 2 out front, 2x squared, and then from 0 to 6. So lastly, we'll get 24 times 6 minus 2 times 36 minus, when we plug in 0, we're going to get 0 from both terms there. So we will get 144 minus 72, and that just happens to give us 72 units for our volume for our object. Okay, everyone, hopefully this gives you a good idea of how to do volumes with double integrals using a function inside to be the height of your function, or integrating between two surfaces, top minus bottom. Thanks for watching. We'll see you in the next video.